Higher physics, particles and waves with diffraction grating. Key areas: the relationship between wavelength, distance between sources, and the distance from sources with the spacing between maxima and minima. The relationship between grating spacing, wavelength, and angle between the maxima. What we will do today: state the equation to describe the relationship between grating spacing, wavelength, and angle to the maxima. Carry out calculations on the above, and state the relationship between the wavelength, distance between the sources, distance from the sources, and the spacing between maxima or minima. The grating and monochromatic light. Monochromatic light is light of only one color, that is, only one frequency. A grating consists of many equally spaced slits positioned extremely close to each other, for example 300 lines per millimeter, which is a typical value. This means that the grating is made up of lots and lots of small spacings. Light is diffracted through each slit, and interference takes place in a similar fashion to the double slit. Monochromatic light needs to be used because if a white light source is used through a diffraction grating, each frequency of the light would diffract by a slightly different amount and a spectrum would be produced. The advantage of using a grating is that much more light is transmitted through and therefore a clearer interference pattern is seen. Here is a typical setup for a diffraction grating experiment. We have a laser producing the monochromatic light source, going through a grating, and this causes an interference pattern to be seen on the screen. We see the brightest spot at the zero order maxima, and an angle theta can be measured between the zero order line and that maxima. The grating equation. For a grating, the equation we use for points of maxima is m lambda equals d sine theta, where m is the order of the maximum, lambda is the wavelength of light, d is the separation of the slits, and theta is the angle from zero order to the nth maximum. Normally, our units for wavelength and for d would be in meters. However, realistically, because they are on either side of the equation, it doesn't matter as long as they are the same units. For consistency, it's best to keep them into meters. Separation of the slits. D is the distance between the slits on the grating. It's usually very small, for example, 1 times 10 to the negative 6 meters. You can find D if you're given n, the number of slits or lines per meter in the grating. With the equation, D is equal to 1 over n. Now this equation doesn't appear on the relationship sheet, but is really useful. Example. N is equal to 500 lines per millimeter. 500 lines per millimeter means we have 500 times 1000 lines per meter, or 5 times 10 to the 5 lines per meter. D is equal to 1 over n, which is equal to 1 over 5 times 10 to the 5, or 2 times 10 to the negative 6 meters. So this gives us an idea of the separation between the slits. It's going to be a very small number. If the grating equation is rearranged to sine theta equals m lambda over d, then it can be seen that to increase theta, the separation of the maxima, you could either increase the wavelength, that's moved towards the blue to the red, decrease the slit separation, that is have more lines per millimeter, or indeed move the screen further away. Example. Diffraction grating with 300 lines per millimeter is used to produce an interference pattern. The second order maximum is obtained at a diffracted angle of 19 degrees. Calculate the wavelength of the light. Solution. We use the formula m lambda equals d sine theta. First of all, we need to find a value for d. We're given the number of lines per millimeter. We can convert this to find the number of lines per meter. And then that's what we're using to find d. Our order of maxima is 2. Theta is equal to 19 degrees. Using our equation, m lambda equals d sine theta, we substitute the values in, and we find a value of lambda to be 5.4 times 10 to the negative 7 meters. This is a perfectly acceptable answer. However, you should note that quite often wavelengths are quoted in nanometers. And with this value of the wavelength, you'd be able to refer to the datasheet at the front of the paper in order to determine the color of light. 2006 paper, question 27b. Light from a different LED is passed through grating as shown below. We can see the light is going through the grating and producing several maxima. Light from this LED has a wavelength of 6.35 times 10 to the negative 7 meters. The spacing between the lines in the grating is 5 times 10 to the negative 6 meters. Calculate the angle between the central maximum and the second order maximum. Okay. So we know our equation is equal to m lambda is equal to d sine theta. A useful rearrangement of this equation is sine theta is equal to m lambda over d. Now this isn't how it appears on the relationship sheet, but should take note of it because it's a useful equation. I'm going to use it here. Sine theta is equal to m lambda over d, which is 2 times 6.35 times 10 to the negative 7 divided by 5.0 times 10 to the negative 6. That means theta is equal to the inverse sine of this, which gives us a value of 14.7 degrees. Note, we must have the degree symbol. 15 degrees would also be accepted. 2005 question 28b, similar diagram. We have white light passing through a red filter to produce monochromatic red light. This goes through a grating, again producing points on the screen which are bright. A pattern of bright and dark fringes is observed on the screen. The grating has 300 lines per millimeter, and the wavelength of the red light is 650 nanometers. First thing we need to do is explain how the bright fringes are produced. So the bright fringes are produced because we have points of maxima. This is a very common question, and we should be prepared for it. So we say that the coherent waves meet in phase producing maxima due to constructive interference. So we have all of the key words here that you would need for your answer. Part 2, calculate the angle of the second order maxima. This is very similar to the previous question. So again, I'm going to go into my rearranged equation. So this is part 2. And I'm going to say that the sine of theta is equal to m lambda over d. In fact, I'm going to go one step further, and I'm going to say that theta is equal to the inverse sine of m lambda over d. That'll help cut down on our working. From the question, we should know our order of maxima and our wavelength. So m is equal to 2. sine theta. Theta is what we want to find. Our wavelength is equal to 650 times 10 to the negative 9. Separation between the slits. We're told that we have 300 lines per millimeter, which means we have 300,000 lines per meter. So D is equal to 1 over N, which is equal to 1 over 300,000, which is 3.33 times 10 to the negative 6 meters. Let's substitute in. Theta is equal to the inverse sine 2 times 650 times 10 to the negative 9 over 3.33 times 10 to the negative 6. So we're doing it all in one step, makes it easy for us. We end up with 23 degrees. Part 3, it says the red filter is replaced with a blue filter. Describe the effect on the change of the pattern observed. Well, we need to know the difference there between red and blue light in terms of wavelength. So blue light has a much higher frequency, which means it has a much shorter wavelength. So the wavelength for blue is less than the wavelength for red. We can see from our equation sine theta equals m lambda over d that if the wavelength decreases, sine theta decreases. Sine theta, and that's of course theta, decreases. And so in terms of the pattern, we see that the patterns moves closer together. So the bright spots are closer together. (2004) question 28b. In an experiment, laser light of wavelength 633 nanometers is incident on a grating. A series of bright spots are seen on the screen. Place some distance from the grating. The distance between these spots and the central spot is shown. Calculate the number of lines per meter for the grating, and then we're talking about what happens if the laser light is replaced with another laser. We'll get to that in a moment. Let's have a look at the first part of the question. Calculate the number of lines per meter on the grating. So we can see from the diagram we have an angle of 37 degrees between the two first maximas from the central. So I'm just going to add to my diagram here a straight line going to my central maximum. This angle here, theta, the angle between the central maximum and the maxima, is equal to 37 over 2. So that's going to be 18.5 degrees. My order of maxima is 1. The wavelength is given to the question is 633 times 10 to the negative 9 meters, and I want to find D. So m lambda is equal to D sine theta. 1 times lambda, so 633 times 10 to the negative 9 is equal to D multiplied by sine of 18.5. D is equal to 633 times 10 to the negative 9 divided by sine of 18.5, giving us a value of 2 times 10 to the negative 6 meters. The laser is replaced with another laser and the experiment is repeated. With this laser, the bright spots are closer together. How does the wavelength of the light from the laser compare with the original laser? You must justify your answer. Okay, well, if we think about it, we have the bright spots moving closer together, so that means theta has gone down Therefore, sine theta must have also gone down. Now, if sine theta has gone down, think about the equation. Sine theta is equal to m lambda over d. That means that if the order of maxima is the same, the separation between the slits is the same, wavelength must have decreased. So the wavelength of the new source is less than that of the original one, so we're moving towards the blue side of the spectrum. Now we have a look at some questions from the revised higher. 2012 question 28b. A manufacturer claims that a grating consists of 3 times 10 to the 5 lines per meter and is accurate to within plus or minus 2%. Technicians decides to test the claims, so she directs a laser light of a known wavelength, 633 nanometers, onto the grating. So we're looking at very, very common figures here. So 3 times 10 to the 5, 633 nanometers. She measures the angle between the central maximum and the third order maximum to be 35.3. And the first thing we need to do is to calculate the value she obtains for the slit separation of the grating. So we're applying the exact same physics here as we applied in the previous question. First step whenever calculation questions, writing down what you know. We know that m is equal to 3 because it's a third order maxima. We know the wavelength is equal to 633 times 10 to the negative 9 because we're given that within the question. And we know theta is equal to 35.3 degrees because again that's given. We want to find d. So m lambda is equal to d sine theta. 3 times 633 times 10 to the negative 9 is equal to d multiplied by sine of 35.3. d is equal to 3 times 633 times 10 to the negative 9 divided by sine of 35.3 degrees, giving us a separation of 3.29 times 10 to the negative 6 meters. We're then asked to say, what value does it determine for the number of lines per meter for the grating? So we've kept this line here. That's our separation between the slits. The number of lines per meter for the grating, remember d is equal to 1 over n. So that means n is equal to 1 over d, which is 1 divided by 3.29 times 10 to the negative 6, giving us a value of 3.04 or 3.0 times 10 to the 5. No units. Okay, so does the technician's value for the number of lines per meter agree with the manufacturer's claim? That is, that the lines per meter is 3.00 times 10 to the 5 plus or minus 2%. So we need to find out how much more our value is to the manufacturer's claim. So we're just looking at the difference between them. So 3.04 times 10 to the 5, take away 3.00 times 10 to the 5, giving us a value of 0.04 times 10 to the 5 lines per meter. We then work out what this value is as a percentage of the manufacturer's claim. So the percentage is equal to 0.04 times 10 to the 5 over 3.00 times 10 to the 5, and that works out to be 1.33%. So 1.33% is less than 2%. Therefore, we can say the technician's value does agree. So you always have to remember with these kinds of questions, you need that final statement to tell me to actually answer the question that's being asked, as opposed to just working out a number. You need the comparison. Okay, so in our final example, we're looking at the 2013 Revised Higher Paper, question 28b. We have an experiment where a monochromatic light is being placed through the grating. An interference pattern is produced on the screen. The edges of the screen are at an angle of 40 degrees to the center of the grating as shown. We're given information on the wavelength of the light, the separation between the slits, and what we need to do is to find the total number of maxima visible on the screen. So that angle represents the maximum angle that light could be diffracted by. So this is a difficult question. Go back to basic principles, writing down what we know. We know that the wavelength is equal to 420 times 10 to the negative 9 meters. We know that the separation between the slits is 3.27 times 10 to the negative 6. And we also are given the maximum angle, which is 40 degrees. So with this information here, it should lead us into what we need to do. This is to try and find our m, the value of our maxima. So our equation is as it stands, m lambda is equal to d sine theta. So m multiplied by 420 times 10 to the negative 9 is equal to 3.27 times 10 to the negative 6 multiplied by sine of 40. So a little bit of rearrangement required here. M is equal to 3.27 times 10 to the negative 6 multiplied by sine of 40 divided by 420 times 10 to the negative 9. Which gives us an approximate value of 5. Now, that's not the final answer. We're told that m is equal to 5, so that we have 5 maximas up to the edge of the screen here. Now, if we have 5 maximas up to the edge at the top, we also have 5 maximas going to the bottom, plus our central maxima in the middle. So remember, we'd have 1, 2, 3, 4, and then 5. So that means the total number of maxima is equal to 5 above 0 plus 5 below 0 plus the central equals 11. So this is a difficult question. It's a difficult question. There's no reason why you shouldn't be able to get 3 marks out of 4 for this just by working out the order of maxima. However, getting that final value of 11 for the total number of maxima, that's going to be an A-type question.